Okay, hello everybody. It's good to see you again, and let's continue our applications to marine debris. As we discussed yesterday, marine debris becomes kind of global problem. It's basically seen everywhere, and one reason why we don't know so much about its life cycle and its balance is because it's very difficult to track common marine debris. Objects in this global economy, plastic items, they are nearly same in different countries and on different continents, and in very short time, all these local marks made in this country, consumed in this country, they just disappear, and whatever you find, it's really hard to tell where did it come from. So ideally, we would need, also when collecting data from shoreline, it's again same story. It's a mixture of so many different things with basically unknown origin. And in that sense, disasters, natural disasters and accidents, they provide unique data. They generate kind of drifting objects that do not exist in the ocean without these events. And in many cases, these objects can be traced back to their origin. And in other cases, amount of debris produced is unprecedented, and then impact of this event can be seen as, increase in long-term timelines. I'm sure you remember this disaster that happened in Japan, March 11, 2011. It was a major tsunami of magnitude over 9 units, and it hit east coast of Japan, several prefectures, and I'm sure you all remember this crisis, Fukushima crisis, which was actually further south. These waves of tsunami, they actually had major effect on lives of people in eastern Japan. It caused more than 15,000 casualties and destroyed more than 100,000 houses. Tsunami wave then propagated across North Pacific. And when we are saying tsunami wave, just by watching video, it does not feel like a wave. It feels more like a flooding. It goes in and in and in as far as topography allows, terrain allows. And on the way, it breaks everything. And then retreating water takes this debris into the ocean and leaves it to currents and winds. In few hours after tsunami, these waves, this flooding, produced 1.5 million tons. And if you remember previous estimate of common debris, general debris, 8 million tons of plastic per year globally, then probably this number is comparable to annual balance of entire North Pacific in a year. And that was produced in small area, relatively small area, in few hours. So this was major injection of debris. In addition, this was not exactly what we see in the ocean in common life. It was when Curtis Ebbesmeyer was asked what is the composition of tsunami debris, he gave very good answer. He said, imagine your town, you take everything and you put it into a huge grinder, and this is it. This is what is in the ocean. So there were floating houses, ships, boats, and everything. So as you can see on these photographs taken by Japanese Coast Guard and US Navy, who were helping during Operation Tomodachi. These, amazing, heartbreaking photographs, they were taken during first weeks when debris was floating close to the coastline. But then 1 month later, nothing. It drifted away from shoreline, and nothing. It disappeared. And at that time, I had a chance to participate in interagency discussions. What should we do? And most of federal US agencies, they were kind of inclined to do nothing. And the argument was that, okay, this is marine debris. Marine debris is always there. This is just another addition. And also, you see this color of these rafts of debris. It's kind of yellow, which means this is wood from broken houses. Wood does not float for a long time. 2 months from now, it will just sink down and it will disappear from the surface. So nothing needs to be done. And it was, to me, it was kind of eye-opening nature experiment showing the level of our observing system. 1 million tons disappear. And at that time, we were trying to reach US Coast Guard, to reach National Science Foundation, to get some funding, to at least go and validate that there is nothing floating there. And then suddenly in June there was some wow email from married couple sailing from Okinawa to Aleutian Islands, and they just ran through this kind of field of debris. And then we were lucky, there was Russian sail training ship with 200 cadets in Honolulu on its way back to Vladivostok. And we spoke with the captain, and we got him concerned, I would say scared, because ship is big but it's vulnerable. And he had 200 young eyes, pairs of eyes. So he arranged continuous watch, and amazingly, right west of Midway, they picked the first tsunami boat, and later this boat was traced back to the owner in Japan. Unfortunately, the owner did not survive tsunami. But what is most important, they observed floating objects all the way to Japan with maximum concentration around here. And here, their reports are overlaid on our, at that time, very primitive model. Just particles with properties of actual drifters. Model kind of what I showed you yesterday. So then we organized, we raised some small funding with private foundation, and we found volunteers who decided to sail to observe this impact of tsunami debris on Midway. And because it was wintertime, it was December, it was really stormy, and they could not reach exactly to the area of interest, but where they were, they did not see tsunami debris. And that was puzzling, because kind of model was predicting that it must hit Midway. So at that time we realized that we don't have observing system of marine debris, and we cannot accomplish much without adequate models. And we also realized that modeling is going to be difficult. As we mentioned yesterday, different models, they give somewhat different results when applied to surface drift. So after receiving grant from Japanese government through North Pacific Marine Science Foundation, PICES, we started working with a team of modelers from Japan and also from NOAA. NOAA response and restoration team, they are responsible for operational coordination of oil spill response. And they use so-called NOM system, which is based on US Federal HICOM model, and then NOAA blended sea winds. So this is not just a model, this is system. This includes particles, this includes additional processes to describe changes of properties of oil. This includes some ad hoc parameterization of beaching and backwashing in the ocean processes and so forth. So we didn't, just to compare the output, we decided we are not going to run this model. We are going just to let the oil spill team to do this. And Amy McFadden did this for this project. Then Japanese government, right after tsunami, started a massive program that included numerical simulations of debris, but focus of this project was in the Western Pacific, which is so west of the dateline, which is area of responsibility of Japan. And so we used their data. Their calculation extended through July 2013. They made some forecast for a couple of years, which was not so good. I will not mention it. And then later, much later, when we were working together, they also produced reanalysis, 30 years of reanalysis. And the difference between these models, they both are assimilating models, and this is 3D VAR, and this is 4D VAR. Assimilation. And on our half, we produced our own simple conceptual diagnostic model, which I will mention in more details next. And that model is based, its resolution, it works, we find it works pretty well for open ocean. But its resolution is dictated by resolution of altimetry and wind, which is quarter degree, so it may be not so good in coastal areas. So to improve in coastal areas, we blended our model after some tuning with HiCom, only in 100-mile band along all coastlines. For our model, our logic was, okay, it's difficult to simulate this complex dynamics in the upper ocean, but we have we have drifters, they are moving under influence of combination of all these processes. So if we start our model without understanding the dynamics, we will just start with their trajectories, and all complex dynamics already included in these trajectories, then we can build on it. As I showed yesterday, instantaneous distributions of drifters are pretty sparse. But if we go to historical data, then drifters cover, with the exception of some inner seas, drifters cover pretty much global ocean between minus 60 south to 60 north degrees. And here, this is number of fixes, 6 hourly fixes from drifter data on 1/8 degree. This is mistake. This is not 1/4, but 1/8 degrees. So 95% of beans are filled with historical data at least once. So then what we can do, we can make very simple assumption. So we focus on currents that are a combination of geostrophic currents and ageostrophic, which in turn are function of local wind. This includes Ekman drift, this includes wind waves, Stokes drift. We assume linearity. In reality, it will be different, and there are many other complications that we neglect. But the way that we take it, actually, we accept these limitations, which means we do not go into scales smaller than deformation radius, and we do not go. We address more like time scales of a week and longer. But on these scales, we hope to get dynamically consistent results. And in addition to address this difference between different floating objects, difference in their shape, buoyancy, geometry from drifters, we also add windage, so-called windage, which is a coefficient that shows what fraction of wind vector, local wind vector, should be added to ocean drift. And coefficients of the model, they are calculated locally on a quarter-degree grid, and then applied to real-time altimetry and scatterometry data combined with mean dynamic topography to produce near real-time currents. In order to compare, to make comparison between all models consistent, we worked with our partners to unify the source function. So we took data on broken houses, broken homes, and after smoothing, we produced some source function east of Japan. And then we ran our models under the same or similar range of windage parameters. And then we applied very similar analysis. In case when we needed to compare, or in case of Japanese model, we just took their velocities and wind, and we launched our tracer. And the same way we used tracer in our model. In case of NOAA, NOM, they are using particles. So we requested to increase the number of particles compared to what they had during when they were producing these updates on tsunami debris distribution for ships, for agencies. We requested increase from 40,000 to 400,000. And that really overloaded their computers, but they did it for us. And then we, instead of counting number of particles in some bins, we actually just smeared every particle with some Bell function over some radius. And then this way, we everything converted into concentration of the traces. So here is one computer movie that covers 5 years, first years after tsunami. All windages are combined together, and difference between them is in colors. So what you will see, red colors are high windage, and blue colors are low windage. 5 years will run pretty fast. I will try to play it a couple of times, but don't worry if you don't catch it, because on the next slide I will just have some frames, and I will walk through these frames. Five years again. So what do we see on these simulations? We see that different types of debris, they should be moving very differently. In the beginning, both currents and winds were pushing debris eastward, and wind was accelerating high windage debris, so that by the end of 2011, high windage hit Alaska and British Columbia. And this is consistent with timeline of observations from these areas. Then, after that, high windage debris was mostly gone, cleared from the ocean by the end of, by the beginning of 2012. Then medium windage debris recirculated towards Hawaii. And this is another conclusion. Debris came to Hawaii not directly from the west, but from the east. That's why our expedition could not find it near Midway. And then after more circulation around subtropical gyre, in the end, low windage debris, it collects in the same area as microplastics, garbage patch. And it's probably going to stay there for a long time. How about other models? How do they perform? Dynamics that they reveal is very similar, if not same. So in the beginning, in the first year, you see how debris of different windages get stratified, and high windage moves faster, a little bit more fuzzy picture. In a NOM model, maybe we should smooth more. But you can see actually it's a little bit different because high windage is all distributed all around the northern edge of the cloud. But this correspondence is not this good for later time moments. So, for example, 2 years later, 2 years after tsunami, you can see how basically location of clouds. So these two models are similar. These are just our models. And you can see how extent of some features, it's different in Japanese models. And its location is really quite different in NOAA NOM system. And this is remarkable that and unfortunately, these solutions, we can only run hindcast. We cannot run forecast. So it was done generally last year. And unfortunately, only then we see that what was distributed by NOAA in real time, it's not very much consistent with our current understanding. So even though they were trying to provide only very general information, like this is risky area, location of this area is not very consistent with what more recent models show. Then, okay, we have 5 models. We have 61 windage. So what? How can we validate our results, our conclusions? We need to compare with observations. Was there any signal from tsunami debris in North America and in Hawaii, or it was nothing, as agents suggested? So there was huge signal. This is timeline. This timeline is just from regular coastal monitoring in three states, and this includes all objects, so all same plastic, general types of debris that cannot be traced back to Japan. People were just counting. And you can see how a little bit, 1.5 years after tsunami in these areas, counts just popped up to the level that was never observed before. So this was clearly, even though it was impossible to prove this is from Japan, but looking at this timeline, I think it's very convincing. But this includes, again, all objects. It does not really help to validate anything because it's all windages. So how about focusing on one category? And we found that a very convenient, in many senses, category is boats, small vessels. They are convenient for many reasons. They, as a rule, okay, without disasters, there are not so many boats lost at sea, floating at sea. Most of them, they still carry readable identification numbers, and they can be validated. Their source can be validated. And then also, the way how they're built, they can survive at sea for a long time. So basically, physical decay, chemical degradation, it can be neglected for a while. So they are kind of perfect conservative tracer. So this map shows location and times of 327 reports on the boats. Colors here show time, these years. And you can see how purple becomes blue and then green and then yellow and sometimes red as observations shift towards east. And then many observations on US-Canada West Coast and in Hawaii. So this is just estimated propagation of center of mass of observations in different years. But this map, it also reveals big problem with such opportunistic observations. People at sea, they report, even if they are motivated, they report only in case if they see something. They see boat, if they know what it is, if they know this is important, they report. If they don't see anything, they don't report. But empty areas, they are as important as areas with debris for validation of the model, because basically what we are trying to validate is a pattern, contrast between high density and high concentration, low concentration. And these data are not available. And because of that, this map is a function not only of location of tsunami boats, but also function of availability of observers. And you can see some features such as along date line, not so many reports, and this is boundary between Japanese and American areas of responsibility, and so I think this explains this gap. And also, as you could see on computer maps, there was some pathway going, debris going this way, and there are some reports from this coastline kind of assuming this path, but no reports at sea, because there is nobody there to report. Anyway, with this kind of heterogeneous and imperfect data set, can we do something quantitative to validate our models? We thought, yes, probably we can. And the idea is the following. Imagine that you have observations, stars, and you have different model runs. It can be different vintages, it can be different models. And then as you run, as time goes, real particles, they say, are moving this way, and different model solutions are moving, kind of accumulating differences between themselves. And so in that case, at this moment, what we can do, we can subsample model concentration at location of actual reports, and model that will collect the highest sum wins. Model solution that was actually not sampled by actual observations loses. So we started playing, and I think this is original idea, but it definitely requires further development, because model concentration, it's model tracer concentration, it's hugely heterogeneous. For example, if you run a high-resolution model, then you will have streamers with very high concentration, and between them you will have very small concentration. And depending where your observation is located, which is often not accurate, your result will be jumping. So some additional thinking needs to be given to this method, but there is something useful in here. So most of models, when applied to the first year, they show some maximum at some intermediate vintage value, and applied for later years, another intermediate value, and this following year vintage is slightly lower than in the beginning, which may be making sense, because all processes of biofouling, degradation, filling with water, they all work to reduce vintage of the object. But it's still very, very uncertain. The best result that I think we obtained came from observations on this stretch of North American coastline. And this is because, look at this timeline diagram. This is time, this is latitude. This is the coastline and distribution of reports. But look at this, look how waves of boats coming on West Coast, how they are synchronous in very broad range of latitudes. This is kind of amazing, but we can use it. This tells us that West Coast acted mostly like a wall, and this justifies averaging in latitude and improving kind of reducing noise in observations. So this is smooth timeline of observations, and note these 5 peaks. And then we take our model and same stretch of coastline, and we calculate a timeline of model fluxes, onshore fluxes for different windages. And this is for our model SCAD, and you can see how high windages, they came first, but then you can also see very interesting kind of maxima, which are kind of seasonal, but kind of not exactly. There are interrennial differences. And then if we smooth, with the same filter as we smoothed observational timeline, then we can try to determine single optimal windage value for which model agrees best with observations. So again, purple here is 5 observational peaks that you saw before, and white are peaks, model peaks for different windage values, and at this value, approximately 1.7, there is pretty nice correspondence. And this correspondence is not perfect for all models, even though solution in the water look somewhat similar. For example, again, this is NOM based on HiCom, and you can see how, well, first of all, you can see how sharp are the events of landing. They occur really in short periods of time. And when we try to compare with observations, it's basically difficult to identify just one single windage parameter that would catch all peaks. So anyway, just by minimizing the deviation, we put together timelines from all models, and this is what we get. Black line in the background is observations, and you can see how NOM, it basically misses with this kind of optimization of windage. It basically misses 2 first peaks and then catches only number 3 and number 5. Japanese model performs better, but it still misses the first peak. And amazingly, our simplistic, I would say still simplistic, very applied model, it captures basically all peaks. There can be questions to amplitudes, but the events are there. And also curiously, when we compare between pure SCAD and SCAD blended with HiCom, HiCom actually makes it a little bit worse. And then other comparison is how boat reports and model tracer, how it was distributed along the shoreline as a function of latitude. So black is observations, and you can see more steep maximum around 46 models. All models kind of show also higher values, but not as pronounced peak as in observations. For now, I do not know exactly the reason. It can be a problem with simulating coastal dynamics. It can be, or it may be something on a larger scale. Then dissipation of tracer with this optimal windage in different models, it looks like this. And you can see, as I showed before, events of tracer landing in NOAA NOM, they're very sharp, very steep, and between there is no decay. So tracer stays basically offshore, then suddenly hits it, then retreats back into the ocean, and it decays at the slowest rate compared to other models. So you can see that there is decay, there is large dispersion between decay estimate in different models. But by the end of 2016, there is still something in the ocean. So now when we now when we have this optimal windage, we can calibrate our models, convert model units into actual units, boat count, number of boats per unit area in the ocean. We can convert into number of boats that arrived in different regions. And this allowed us to estimate that original number of boats generated by the tsunami was approximately 1,000. And this is consistent with estimates of Japanese Coast Guard. And with this number, approximately 100 boats we expect to be still floating in the ocean. And because boats that we find, they come in excellent condition, we think they will continue coming. They are not going to sink down. And in confirmation of these expectations, this is a photograph of boat that was observed this January of Big Island. It was not recovered because there were sharks in water, but they took many pictures. And you see, it's not broken. Its name was later identified and verified. And when looking at this picture, you know, it gives me this feeling that it is kind of on a mission, that it gently carries something that is inside, like a bowl. And this is often true. In 2012, when one of 4 large docks washed from north of eastern Japan, when the first dock arrived in Oregon, biologists, they've got unique opportunity to collect samples from this dock. This is 20-meter large dock. And what they found, more than 100 Japanese species that survived the travel. That was amazing, and that was kind of first discovery, first kind of proven opportunity to find Japanese, first proof of possibility of pan-Pacific travel. So after that, they started collecting data from smaller and smaller and smaller objects. So original idea was that dock is special because it was in water and it was colonized before drifting away. It was large enough to accommodate, you know, large communities. That is important, maybe important for survival. But then alien species, Japanese species, were found on smaller and smaller and smaller and smaller objects. And this paper was published in Science magazine just last month. And Jim Carlton and his colleagues, they reported, they documented many species. And this is where we've got this unique opportunity to contribute with our experience with ocean dynamics. So if this is, we decided to help to understand how this, to estimate probability, how this species can survive travel and whether they can actually establish in North America and or in Hawaii. And we found out that this is kind of unique situation when area affected by tsunami east of Japan, it corresponds to the greatest range of temperatures in seasonal cycle. So summers are hot and winters are very cold. So basically, and temperature is the parameter that, you know, kills most quickly. So it appears that species originating from east of Japan, they could travel easily within the comfortable range of temperatures all the way almost to any place in North America. Hawaii is kind of exception, but then what is interesting, on that dock, they found not only cold water species, but also warm water species. And there were indications that this dock was observed actually very close to this Kuroshio extension. And it was very possible that it got in touch here with warm water, and it got on board warm water species. And if this is the case, then warm water species, oh, they would find Hawaii as a paradise. To help estimate probable trajectory, we developed, I view it as a new technology. Usually, as you know, people describing drift, they use particles in their models. And this is kind of natural way to represent solid debris. It's indeed like a particle, but particles, they have very, very bad property. They disperse broadly. And when you are trying to, and so you need more and more particles to fill gaps, and then in many areas particles come together, and simulations, they kind of replicate each other, and CPU time is used not efficiently. So we switched, as I mentioned before, from particles to model tracer and tracer concentration. So we release dye at start point, and then we interpret concentration of this tracer as a probability density function for model particles to come to this location at this time. And this actually gives us opportunity to use powerful apparatus of probability theory, mathematical apparatus. So now, when we have this PDF, we can calculate probable trajectory, we can calculate probable parameters such as sea state, temperature, salinity, anything along this probable trajectory. And then similarly, if we only know the end point, we can run it backward, and we can estimate probable trajectory that led to this destination, and also we can estimate probable origin of this object. And again, it's probable in terms of probability, so we can put numbers in percents where it possibly came from. But in fact, we can do more. Now we can combine probabilities. For example, if we know that boat started from point A and ended at point B, then we can estimate its probable location during some intermediate time. And this is easy. We just run forward from start point, we run backward from B point, and then we estimate probability for the particle to start from point A to B at intermediate time at this location, and end at end time at point B. Then from here, it's just one step to probable trajectories. For example, if we this is just multiplication, mathematical, logical, and multiplication of two PDFs. And now, if we integrate these PDFs in time, then we can isolate locations where probability is high that they were visited on the way between A and B. And you know, I would still expect that solution probability should be fanning, kind of broadening wildly from start point and then from end point, and there should be huge uncertainty between them. No, this is not what we see, and this is amazing. And I think, so this is example of the second dock, twin dock, that ended 1 year, half year later in Washington State. And this is example, so this is forward simulation, backward simulation. This is product of these two as a probability of location at intermediate time moment. And then this is integral of these PDFs. And you can see it's kind of amazingly narrow. And I think one important role that is important role here is played by timing. So it's not only location that you know, allows particles to spread. It's also timing. Particles should arrive at exact time at destination, and this keeps probably this path pretty narrow. And we ran many calculations with this technique, and some trajectories are quite amazing. So this boat, this is small research boat, it started from Japan and it ended in Japan, in Okinawa, after 5 years of drift all around the ocean. So when a group of Carleton, when they published this paper, there is one amazing fact that they recognized. So Japanese species continue coming to North America and to Hawaii, and amazingly, some of them are younger than 5 years, than 6 years that passed since tsunami. And because we know for sure there was no additional source of debris from Japan. Japanese government cleaned coastline pretty fast. So this means they're coming from somewhere else. And from our model, we know that the only place where debris still can be is garbage patch. So this points us to very interesting idea that coastal species somehow survive and and even more importantly replicate in this pelagic ocean. So that's why I'm so glad to let you know that we are starting a NASA-funded project on interdisciplinary science team where we will partner with Scripps Institution, Smithsonian Institution, Applied Physics Laboratory. We will go to this area of garbage patch. We will deploy scientific equipment to measure drift of different types of debris. We will attach trackers to real debris. And we will deploy biological panels. And then we will collect all these samples and also samples of debris. And we will be looking for coastal species. So the idea is that this pulse of debris from tsunami, it probably added new substrate that created a new type of ecosystem in the open ocean. Am I out of time? Then maybe I should stop here. You can check a few left slides on the Google Drive. But in the end, if I can, just a couple of philosophical statements. Before coming here, I attended a small workshop in Barcelona, MapMass, which stands for Marine Pollution and Marine Safety, where I spoke with Coast Guard and some centers coordinating activity like search and rescue. And I was told, off Spanish coastline, probability of being rescued is approximately 99.997. Okay, so I listen this and I feel like this is not my planet. I'm not needed. It's already perfect. And then I look back and I remember 1 million tons of debris disappeared. And then on slides that I will not show you, Mexican fisherman was drifted unnoticed for 14 months. And then a Malaysian airplane, with all the effort, it's not found. And this is where I feel home. This is where I feel like I'm needed. And I hope you will share this feeling and you will contribute. And if you work in the Mediterranean, please go and check what is wrong with that statement, because it's just, I don't know, it cannot be. And second thing, I was asked by Ananda what kind of motto we could suggest to you, young scientists. You saw how different vintages are moving. So if you sit low in water, you will be sucked into some ugly garbage patch, and you will stay there maybe forever. But if you kind of high windage, then you have good chance to be blown by wind on some nice solid land. So my advice to you, keep your windage high, okay?